Hi everyone, we're going to find the intervals on which f is increasing or decreasing, find our local max and min values of f, and find the intervals of concavity and inflection points. So this one's a bit of a harder problem, mainly due to the algebra. So we need to talk a little bit about what does our derivative say about f, and that's based off our increasing and decreasing test. So if the derivative is positive on the interval, then f is increasing. If the derivative is negative on the interval, then it's decreasing, and that's what that little bit says there. So we have to find the intervals, and we take the first derivative. We're going to use the quotient rule. So you copy down the denominator and multiply it by the derivative of the numerator, which is just 1. Subtract, copy down the numerator, and multiply that by the derivative of the denominator, which is 2x. And then you take your denominator and square it. Now simplifying the numerator, we're going to get x squared plus 1 minus 2x squared over our denominator. So that's going to eventually give us 1 minus x squared divided by x squared plus 1 squared. This can be factored more, 1 minus x and 1 plus x divided by our denominator. All right, and then we set that to 0. To cross multiply, the denominator goes away. So our critical values are x equals 1, x equals negative 1. Therefore, our intervals are going to be like this. You put the negative 1, if this is our x and 1. And we want to know on the graph, we're not graphing these, but on the graph, what's going on with our interval when x is less than negative 1. So this piece of the graph. And what's going on between negative 1 and 1, and what's happening when x is greater than 1. So those are the intervals we're going to use. Now, I'm going to do an interval chart. So we already found our intervals. So we have when x is less than negative 1, when x is in between negative 1 and 1, and when x is bigger than 1. All right. Now, we had, for our intervals, we had 1 minus x, 1 plus x, and then we had our denominator equals 0. So what I'm going to do is write these down. This is kind of like extending it. We could do some of this in our head. 1 plus x, and see what's going on with our first derivative. And that's going to tell us about our graph of f. So when x is negative 1 or less than negative 1, so say if I put in a negative 2 here, this is going to make this a positive. If I plug in negative 2 on this one, I'm going to get a negative number. So when you multiply a positive and a negative, you get negative. That tells you, let me put a little double line here. Since it's negative, that means it's decreasing on interval negative infinity and 1. All right. Now let's try 0, because 0 is in between negative 1 and 1. So if I plug in 0 here, I get positive. If I plug in 0 here, I get positive. A positive times a positive is positive. That means our graph is increasing on the interval negative 1 to 1. All right, and then greater than 1. So if I plug in a 2 in these, this is going to make this negative. This is going to be positive. So a negative times a positive is negative. So that means decreasing on the interval 1 to infinity. So now that we have that information, we can find our local max and min. So for what it states is for your first derivative test, if it changes from positive negative, then we have f has a local maximum at c. So basically f prime of x is positive at, let's see, -1, 1. And f prime of x is negative at intervals -infinity to 1 and 1 to infinity. So what we're going to look at is where it's increasing and decreasing. So from here, it's decreasing to increasing. So decreasing to increasing, some kind of curve like that. That means at 1, that should be -1. At -1, it's going to be a minimum. So f of -1, now you plug the -1 back into this original function, and you're going to get -1/2. So that's going to be a local minimum. All right, and then we are increasing to decreasing. So that means increasing to decreasing. And that's happening here at 1. So we do f of 1 equals 1/2, and that means it's a local max. So that's the first two. Now, the part that's going to be the hard part is the intervals of concavity, and then finding the inflection points. And it's mainly because of the algebra. So we're going to take our equation, our first derivative. So let's write down our first derivative was 1, let's put f prime of x, okay, was 1 minus x squared divided by x squared plus 1 squared. So now we have to take the derivative of this using the quotient rule. So a second derivative. So what you do is you copy down the denominator times the derivative of the numerator, which is -2x, minus copy down the numerator times the derivative of the denominator, and use the chain rule. So it's going to be 2 times x squared plus 1 times the derivative of the inner function, which is 2x. And then you have your new denominator is going to be x squared plus 1 squared, and then you square that again. All right. Now we have to clean up the numerator. And what makes this hard is you have to do your common highest common factor or greatest common factor and pull it out. So we have basically two pieces here, and we need to pull out what's common to these. So we can pull out, you see this negative? If I pull out a -2x, I'm going to pull that out. That's common to both pieces. I can change this to a negative and make that a positive. Okay, so that way it'll be the same. We also have x squared plus 1. So pick your smallest one. So that's going to be x squared plus 1. All right, so we have that piece. Now we're going to multiply it by whatever's left. So we still, for this first piece, have x squared plus 1. And then for the second piece, I'm going to have this 2 and then times that, 1 minus x squared. All right, now all we have to do, and then we still have our denominator, so I'm just going to put d for denominator. Now let's clean that up some more. So we have negative 2x times x squared plus 1. And this piece here is going to simplify as x squared plus 1 plus 2 minus 2x squared. So that's going to give you this part here. Let me fix that. That's going to give you negative x squared plus 3. Now, what I can do is, before I continue, I'm just going to put the denominator here. What I can do is pull out this negative and write this as x squared minus 3. That way I can take these two negatives and make this a positive. Okay, so I'm going to do that on the other slide. So make sure you have this written down. So now we're going to have this, and this is going to be positive, and you're going to get 2x times x squared plus 1 times x squared minus 3 all over x squared plus 1 to the 4th. Okay, now what happens is, since we have 2 of these, I can reduce this. That will cancel, and this will change to 3. So basically what we have is 2x times x squared minus 3 divided by x squared plus 1 cubed. Now set that to 0, and you have x equals 0. And for this one, you saw for x squared minus 3 equals 0 is x squared equals 3. Square root both sides, do plus and minus, so you get x equals plus or minus 3. Or square root of 3, sorry. So if I do a little graph here, I'm going to get negative square root of 3, 0, and square root of 3. So I have 4 intervals. I have x is less than negative square root of 3, x is in between negative square root of 3 and 0, x is in between 0 and square root of 3, and x is greater than square root of 3. So those are the intervals I'm going to use on the next slide. And then we're going to look at this equation here. All right, so let's start with that. I'm going to duplicate page. So I'm going to do my intervals as x is less than negative square root of 3. X is in between negative square root of 3 and 0. X is in between 0 and square root of 3. And x is bigger than square root of 3. Now, I'm just going to do this more mentally here and just copy down my equation, which was 2x times x squared minus 3 divided by x squared plus 1 cubed. Now, I'm going to see what's going on with my second derivative of x. All right. And that's going to tell us if it's concave up or down. So if I plug in, let's say this is negative, square root of 3 is approximately 1.73. So let's say I plug in a negative 2. If I plug in a negative 2 into this equation, the whole thing is going to be negative. So that's going to be, this is going to make our graph, I'm just going to write this as my f. My whole graph is going to be concave down. Now, for this one, let's plug in 1. If I plug in 1 into this whole thing, I'm going to get, let's see, no, I can't plug in 1. Plug in negative 1, you're going to get a positive. So that means it's concave up. All right. And for this one, let's plug in 1. If you plug in 1, you're going to get negative. That means concave down. And if I plug in, say, 2 into this, I'm going to get positive. So that means that's concave up. All right. So now that I have that, I know that we have the concavity up and down. So it's concave up from negative square root of 3. And f of negative square root of 3 is going to be an inflection point. Since it's going down, up, let's see, down, up, down, or up, down, that means we do have inflection points at our x values. And our x values were 0 and plus or minus square root of 3. So for this one, when I plug this in, I'm going to get negative square root of 3 and square root of 3 divided by 4. If I plug in 0, I just get 0, 0. And then let's plug in the positive square root of 3. Or so you go back to your original equation, just plug it in. And that's going to give you square root of 3, comma, what was that? Square root of 3 divided by 4. This should have been negative. Sorry about that. And that's it. Thank you. Have a nice day. Bye-bye.